Okay, so let's talk about electronic configuration, right? So, rules for assign electron configurations and drawing orbitals diagrams for atoms and ions. The first one we needed to understand about Pauli exclusion principle. So no two electrons can have the same energy. That it means cannot have the same exact four quantum numbers. So quantum numbers you're gonna see soon. But first, let's understand about electron configuration. So according to Aufbau principle, electrons will fill atomic orbitals of lower energy before filling higher energy orbitals. That makes sense, right? First, the one in lower energy, then the one highest energy. Next is Rundle's principle, Rundle's rule. Orbitals in the same sublevel will be half filled one electron in each orbital before the electrons will be paired. Okay, so everything this number here. So 1 SC2, let me see here. The first one start with 1 SC2. 1, 2, 3, the first number here are the electronic configuration. Then the later, like S, P, D, F are the kind of orbitals. And the numbers on the top here are the electrons, number of electrons. Right? So, for example, 1 SC2 here, energy level 1, S, the orbital S, the kind S, and it 2 the electrons. So, 1 SC2. This arrow here is showing the direction. So first, 1 SC2, then 2 SC2, then 2p6, 3 SC2, and then go in this order here. For example, to write the electron configuration for like oxygen. Oxygen, right? You have the atomic number is 8. So 8 electrons. So the first one, 1 SC2. We need to find to do until we have 8 electrons. So first now only 2 electrons, right? And we have the next one, 2 SC2, 2 plus 2. So we have 4 electrons, then the next one, 2p6. Oops. If you write 2p6 here, we will have more than 8 electrons, right? So oxygen has only 8, right? So 8 electrons, 2 plus 2, 4, plus 4, 8. So the electron configuration for oxygen is 1 SC2, 2 SC2, 2p4. So the P, the orbital P can have up to 6 electrons. So it cannot go more than 6 electrons, but can write less. Like the S is up to 2, P 6, D up to 10, and F up to 14. So increases in 4, like 2 plus 4, 6, 6 plus 4 plus 4, 10, 10 plus 4, 14. So subshell S, P, D, F. So the subshell also indicates the kind of orbital. Orbitals S, orbital P, D, and F. The first letter here, so the first number indicates the number, the energy level, like energy level 1 and 2. Okay, so the oxygen configuration is this one. But if the question asks, How many electrons you have in the outermost shell? How many valence electrons? So we're going to count all electrons that they are in the highest energy level. So everything in the highest energy level here we have 2. Everything in 2, in that case, will be the numbers of valence electrons. So 2 plus 4. So oxygen has 6 valence electrons. All right, okay. So you can see here, let's that the electron configuration, we are writing, obeying this sequence here, right? This order. 1s2, 2s2, 2p6, 3s2, then 3p6, 4s2, then going on till the maximum of electrons. For example, the last atomic number right here, for example, would be the highest energy level, and then it's the one that has highest atomic number. This 118 atomic number will be the last one. It'll be right here. Okay, let's see another example in the back here. We also have numbers of electrons. For example, hydrogen. Hydrogen has only 1 electron, right? Atomic number is 1, so just 1 electron. So electron configuration for hydrogen is just 1s1. What's the orbital diagram in here? So each orbital, right? So will be writing the electrons using arrows here to represent each electron. For example, 1s1 has only 1 electron. Electrons will be arrow up here. So now that you learn about the electron configuration, let's go back to the order here. It's about quantum numbers. So quantum numbers. We discussed that areas of probability as orbitals, which serves to describe the spatial distribution of electrons around the nucleus of an atom. So the s orbitals will be all circle here. They have this region, the electrons, they are moving like this region here. The p orbitals, you have this, the orbitals have like this shape here, causing electron clouds. The orbitals will be a little bit more complex, and the orbitals are more complicated, so it's not here, right? So S, P, D, F are the subshells. That will be each one here is the area that we can find the electrons, orbitals. As orbitals can find this are here, p orbitals, D and F. So each orbital is described by a set of 4 quantum numbers. The quantum numbers are like a GPS to find the electron location, right? Okay, so we have 4 quantum numbers. Then it will depend on the configuration. We'll say, okay. So the first one, principal quantum numbers at the energy level. Principal quantum numbers, energy level. The first number, for example, we showed here, right, the electron configuration for oxygen, like right here. Let's say if the question asks, what are the set of, what's the principal quantum numbers of the less electrons in oxygen? The less electrons are right here. right? So the energy level for oxygen, like N, the last electron, for oxygen will be number 2. The first number, the energy level here. Energy level. So you have 7 energy levels, right? From 1 to 7. Energy level can be from 1 to 7. Then the next one is about angular momentum number. It's about the L that indicates the sublevel of the orbitals. Or subshell, sublevel. The sublevel that indicates the kind of orbitals, actually. Yeah. Orbitals, sorry here, kind of orbitals. So you know that we have 4 orbitals, right? That we saw here. 4 kind of orbitals, they are the subshells, S, P, T, F. So for S, P, D, F. L indicates the angular momentum number. If for S, the L will be 0. For P, it would be number 1. For D, 2. And for F, 3. For example here, what is the L for the last electron for the oxygen here? So L will be the last electron is in the orbital, the subshell P. What's the L number for P? Is number 1, right? Okay, so L will be number 1, right? Okay. So don't forget this. The S, P, D, F are the subshells. They are the kind of orbitals. And the L will be the angular moment number. And for each subshell, L will have a different number. So for S will be 0, P will be 1, D will be 2, and the F will be 3, right? Okay, so right now, the numbers for the last electron, the quantum numbers for the electron, the last electron, the oxygen is N2L1. So you need to find what? MEL and MS. What are the MEL and the MS for the last electron of oxygen here? The magnetic quantum number indicates in which orbital will be located the electron that wants to know the quantum numbers. So magnetic is about which orbital? Which of the orbitals? Okay. Let's go back to electron configuration right here. S, this number here on the top are the numbers of electrons. So the S can hold up to the S up to 2 electrons, P up to 6 electrons, D up to 10 electrons, and F up to 14 electrons. Right? Okay. So MEL here, that will be the magnetic quantum number. S can hold up to 2 electrons, P up to 6, D up to 10, and F up to 14 electrons. So the MEL, you need to draw the orbitals here. You are drawing the orbitals in square using the boxes here. So L for S is 0. And the S fits up to, like, can hold up to 2 electrons. And each orbital fits up, holds up to 2 electrons only. Right, so Fs, you can hold it only up to 2 electrons. How many orbitals do you have? So how many boxes or orbitals you have in for S here? Only one box. That means only one orbital for S. Because S fits up to 2 electrons, right? 4. And the MEL for this one will be right here. And for P holds up to 6 electrons. So how many orbitals will you have for P? It will be 6 divided by 2, right? So 3 orbitals. 1, 2, 3. 3 boxes here. And the number of, so P can hold up to 6 electrons, right? In each box will have only 2 electrons. The range is gonna be from -1 to +1 for MEL. It's too small here for me to draw. You guys can see better. Okay. Right. So let me draw here just so you can see better here, right? Quantum numbers. So S, P, D, F. So S, the subshell S can hold up to 2 electrons, P 6, D 10, and F 14, right? Okay, so the angular momentum number for S will be always 0 here. The L for S will be always 0 for P, 1 for D, 2, and for F, 3. And the third quantum number that are going to be the MEL, about which orbital will be, where, like, which orbital will be the electron they were looking for, right? This resolution improved here. Okay, so MEL is about, okay, but which orbital talking about, right? So the subshell S fits up to 2 electrons only to have just one box. That it means one orbital here. And what's gonna be the MEL for the S? It will be just the 0 here. And each orbital fits up to 2 electrons, one arrow up and another arrow down here. That it means only 2 electrons in each box, 2 electrons in each orbital. The P, subshell P, is up to 6 electrons, right? So we have 3 orbitals. 1, 2, 3. This one is the MEL for S. Okay, so 3 orbitals. And the range for MEL for P will be from -1 to +1. Are you seeing the number here? The L number, the angular momentum number, will also say the range of MEL. MEL is the magnetic quantum number. In other words, in which orbital will be the last electron, right? Okay. So P6, 1 electron, 2, 3. And then you start after you go up and use it all orbitals up, and then you go back and write down, down, down. This is about one of the rules that we talked about, right? That will be the Hund's rule here. Orbitals in the same sublevel will be half filled. That means one electron in each orbital first before the electrons are paired. So first, I write individually arrows up here, up, 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 and then down, down, down. Okay, so for D can open up to 10 electrons. So how many orbitals should we have here? For D, for 10 electrons, 10 divided by 2, so 5 orbitals. And what's going to be the range for MEL? From number 2 indicates it's going to be from -2 to +2. So the orbital -2, -1, 0, +1, and +2. So how going to be the 10 orbitals distributed here? First, you draw all arrows up. 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10. All right. And for 14F, F, how many orbitals will you have in the subshell F? So if F holds up to 14 electrons, that means how many orbitals we're going to have here? So 14 divided by 2, 7 orbitals. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. One more, right? And what's going to be the range here? F is 3. The L for F is 3, right? So we're going to be from -3 to +3. So we're going to be -3, -2, -1, 0, +1, and +2. And the electrons will be distributed out first up, 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 and then we're going to continue. For example, if you needed to do F11, how going to be F11? Okay, let's count it here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if you're gonna find what is the location for the electron number 11 here, the 11th electron will be in the MEL 0. So MEL for F can be from -3 to +3. MEL for D can be from -2 to +2. Right? For P can go from -1 to +1, and MEL for S will be always 0 because the S has only one orbital. So now that you talked about MEL, right here, what will be the MEL for the last electron that you have in the oxygen here? So MEL for P to P. How many orbitals do you have in P? You know that the P is up to 6 electrons. So how many orbitals we have here? We have 3 orbitals, right, for P. P, the first one is -1, then 0, then +1. How many electrons we have in the oxygen here? The last electron here, we have 2p4. So 1, 2, 3, 4. That means the last electron for the oxygen will be the MEL, will gonna be the -1 here. We will count 1, 2, 3. The fourth electron, gonna be this last electron here, is located in the sub orbital -1. So the MEL gonna be -1. And the MES is about spin quantum number. The spin quantum number can be like electron up or down, right? So if MS So for up will be plus 1/2. If the electron is pointed down, will be minus 1/2. Big quantum number. So the last electron for oxygen here is pointing down, so the MES for the last electron oxygen will be minus 1/2. Okay, so this here, I'm still going to continue all the steps here. I just wanted to show how to find the set, the 4 quantum numbers for like the last electron oxygen here. Now, let's continue here. So what you know about quantum numbers? No two electrons in the same atom can have the same set of 4 quantum numbers. Because the 4 quantum numbers are like the GPS, right? So each electron in an atom will have its own location of set of 4 quantum numbers. Therefore, no two electrons in the same atom can have the exact same energy. This means that every electron in an atom must be different by at least one of the 4 quantum numbers values. So N, L, MEL, and MES. Right? Okay. Now the next is energy of orbitals. So a different way to represent the 4 quantum numbers used to describe each electron's location, like using electronic configuration, is a way to represent the arrangement of electrons in an atom or an ion based on 2 quantum numbers. So N is the principal, right? Principal quantum numbers, principal, and L will be the angular momentum number. Momentum number. Okay, and that is so we saw the previous, right? The energy that's the N can change from 1 to 7, and the L, that's angular momentum number, can range from 0 to 3. The principal quantum number is the N, right? And the L is the angular momentum number. The orbital diagram is a way to view the arrangement of electrons in an atom or ion based on 4 quantum numbers. For example, the neutral atom of carbon has atomic number is 6, so we have 6 electrons. What will be the electron configuration for 6? So we can look back, right, the diagram here. So 1s2, 2s2, 2p2. 2 plus 2, 4, plus 2, 6 electron, right? Carbon here has 6 oxygen. 2 in energy level 1, and 4 in energy level 2 here. Right? So, for example, what is going to be the diagram for the carbon? So, S, how many orbitals, so how many electrons have you here? For one S, you have 2, right? So, one up, another down here. For 2s, how many electrons do I have here? 2s, 2. So, okay, one up, another down. And about the 2p, we have a 2p, only 2 electrons, right? 2p2 here. So, going to be one up and up, right? Why I did not write it down or write on the first one? Because we are going to fill everything up until the last orbital. For example, if it was 4 electrons, would 3 here, and the fourth gonna be go back to be upside down. Okay, numbers of orbitals in each subshell, right? So you know the S. S can fit up to 2 electrons, so have one orbital. Fits up to 2 electrons. P, you saw the UP fits up to 6 electrons, right? So you have 3 orbitals. D will have 10 electrons, so have 5 orbitals. And F will have 14 electrons, so have 7 orbitals for F. And let's go back here, review what you saw. Rule for assigning electron configuration and draw orbital diagrams for atoms and ions. We're going to talk more about the electron configuration, use the periodic table on the next video, okay?